Hello, I'll be presenting the work entitled Predictive Online 3D Target Tracking with Population-Based Generative Networks for Image-Guided Radiotherapy. This work was done at Polytechnique Montreal in collaboration with CHUM Research Center. In external beam radiotherapy, motion management is essential to ensure an accurate treatment of moving organs such as liver, lungs, among others. The MR-Linac system enables simultaneous imaging, beam shaping, and delivery. Therefore, it allows monitoring the in-plane motion. However, it lacks volumetric information needed for 3D target tracking. Motion models coupled with temporal predictive mechanisms represent a solution to provide 3D deformations using the in-room surrogates. Therefore, the main objective of this work is to develop and validate an image-driven predictive 4D motion model. Principal component analysis have been widely explored to create respiratory motion models, whether population-based or subject-specific. These models allow to relate high-dimensional deformations with partial observations acquired during treatment, known as surrogates. On the other hand, 2D to 3D deformable registration have also been proposed to derive volumetric information using a static reference volume and real-time images. Presently, deep learning-based architectures has been introduced for the same modeling purpose. In this work, we learn from an ensemble of time-resolved 3D acquisitions covering a wide variability of respiratory patterns. We assume a static volume acquired at certain respiratory phase, typically at exhale, called Vref, a temporal volume acquired at time t, called Vt, and a sequence of images which contain images acquired at times t-1, t-2, up to t-m. The motion observed between the reference phase and other phases can be estimated using deformable image registration, generating a 3D deformation. In this work, we propose a novel approach using deep networks, where the first goal is to compute a mapping between 3D deformation and their low-dimensional representations. The second goal is to relate the surrogate images with 3D deformation in future times. This figure shows the proposed model, which can be divided into functional components, each one designed to accomplish the previously mentioned goals. The model was trained in 3 different steps since jointly address all the tasks would be a challenging problem. In the first step, we leverage the capacity of autoencoders to learn a nonlinear parametric mapping from volume deformations to their latent representations C. We start by defining a future extraction function f implemented through an encoder that computes a compact representation C from the input deformation. Another function g, namely the decoder, maps from the low-dimensional representation back into the input space, thereby reconstructing the DBF. On the other hand, anatomical features are extracted from the reference volume using an auxiliary encoder and fed as compressed skip connections to the decoder. The reference volume is finally warped with the predicted DBF, thereby generating a new volume that is compared with the ground truth volume. The loss function seeks to maximize the similarity between the ground truth and reconstructed volumes, while imposing a regularization to ensure smooth deformation fields. The second part of the model contains the temporal predictor. It receives a sequence of images where each image is concatenated with their corresponding slice in the reference volume. Then they were processed individually by a 2D feature extractor network and fed to recurrent units to predict one or more embeddings corresponding to future time steps. The loss function here seeks to minimize the difference between the low-dimensional representation obtained by the autoencoder and the embedding regressed by the temporal predictor. During the training of this temporal predictor, the weights of the autoencoder remain fixed. In the third step, we combine both models and fine-tune them all together. Our experiments were conducted using 3 different datasets which contain images from healthy volunteers and cancer patients. The volunteer MRI and ultrasound datasets were used for model creation and leave one out validation, whereas the patient data was used as holdout test set. Now I'll present the experiments and results. First, to explore the latent representations created by the model, we compute and visualize the 2 principal components of several samples and observe that they are spread between extreme phases. This behavior was observed both in MRI and ultrasound datasets. This phase discrimination explains the volume generation and is useful to understand the modeling process. This second experiment was aimed at answering the questions of how the model copes with intercycle variations. For this, a single vessel was tracked through several respiratory cycles. The figure illustrates the target and predicted vessel positions as well as the error plot in the superior inferior and anterior posterior motion directions in 3 cases with irregular breathing. We can see that errors remain lower than 3 millimeters and 1 millimeters in both planes. To assess the tracking accuracy of the model, between 5 and 10 blood vessels were manually annotated by an expert. The reference volume was not considered during the error calculation. We compared the results to 2 state-of-the-art techniques, namely a related deep network and a motion extrapolation approach. The first row in this table shows the tracking errors without motion compensation at different respiratory phases and the overall value. It can be observed that the proposed model driven with coronal images was able to compensate these errors. Moreover, we observe a slightly increased performance with respect to the sagittal orientation, which is in line with previous findings. These plots present the error distribution considering all spatiotemporal voxel-wise displacement for the 3 datasets. It can be observed that in all cases, the median errors are smaller than 3 millimeters. Also, the overall compute mean error was 1.78, 1.74, and 1.99 millimeters for volunteer MRI, patient MRI, and ultrasound datasets, respectively. During training, we assumed that the surrogate images were located at the middle of the right hemidiaphragm, because generally this area represents very well the motion. However, this assumption could be difficult, particularly in ultrasound systems, since it depends on the positioning of the probe. Therefore, we evaluate the effect of shifting these positions during model inference. We found that both in MRI and ultrasound datasets, there was no degradation. This means that the model was robust to these potential variations and that predictions were based mainly on phase detection rather than image appearance, which is an important advantage over state-of-the-art solutions. We also evaluated the image quality at different parts of the generated volumes. For this, the volume were divided in 5 subvolumes across the right-left axis. Then we compute the voxel-wise similarity between ground truth and predicted volumes. It can be observed that values are relatively stable across all the subvolumes for both datasets. In the MRI dataset, we observe a slight degradation on the leftmost part, which correspond mostly to skin or other structures that are not interesting for us in the task in question. We assess also the quality of the deformations by computing the Jacobian determinant. And for instance, in the volunteer MRI dataset, 99% of voxels had a non-negative Jacobian determinant. Here we have some qualitative results which demonstrate the volume generation from real-time images. These results correspond to a predicted horizon of 450 milliseconds in the volunteer MRI dataset and with the model driven with coronal slices. We can also observe the out-of-plane difference maps between ground truth and predicted volumes. Here are some general considerations. First, we assume that the preoperative volumes and the surrogate images are rigidly aligned to a common reference space, meaning that they have the same orientation. Second, the model has to be tested with the same field of view as training. Third, although the model was treated as population-based, it can be easily adapted to work on subject-specific conditions. In this case, the model could be personalized with a fine-tuning using temporal samples from the patient. This will lead to a better fit to the patient needs and hence an increased accuracy. Finally, we use the reference volume extracted from the 4D dataset. However, in the clinical setting, it will be acquired independently. Therefore, this aspect should be further validated. Finally, some important take-home messages. The proposed model is real-time applicable since it only needs 8 milliseconds for the inference. The model shows strong generalization capabilities when working with unseen cases. Unlike other methods such as PCA, it doesn't require establishing inter-subject correspondences, a process that can be time-consuming. Also, the model has shown to have characteristics such as robustness to intercycle variations, shifting of the surrogate location, and structured latent space. The obtained accuracy is clinically relevant and comparable to state-of-the-art results while introducing new advantages. Future studies should focus on assessing the impact from a dosimetric point of view and also exploring other temporal predictive mechanisms. Thank you for your attention, and we also thank our collaborator and funding agencies.